Hello everyone, welcome to Pepcoding. So in this video, we are going to discuss the question, count pairs with XOR in a range. So basically, we will be given an integer arrays and two integers, that is low and high, and we have to count the number of pairs for which both of these expressions are satisfied. Which expressions? This. See. So basically, we will be discussing all these points. So let us start. So basically we are given an array of integers. Suppose the integer values are 1, 4, 2, 7, and we are given a low and a high range. So suppose low value is 3 and high value is 5. So basically what we have to count in this, we have to firstly count the pairs, and also that pairs, what kind of pair should it be? It should be the pairs in which, if we have selected two numbers in a pair, then doing the XOR will result in something that should come in a range. So having the XOR of two numbers, that is a pair, will give a result, and that result should be in the range. So that range should be greater than equals to low and less than equals to high. So this is what question is saying. So we have to find all such pairs. Suppose we are given four numbers, that is four integers. So the integers are 1, 4, 2, 7. And if we'll have pairs, if we want to get the pairs, then the pairs will be 1, 4, 1, 2, 1, 7, 4, 2, 4, 7, and 2, 7. See, pairing is done like this: 1, 4, 1, 2, 1, 7. If you say that the pair is also 4, 1, then definitely this is also a pair. But this is the permutation of this pair. So we have to avoid permutations. Okay. So if the pair is 1, 4, then we will not include 4, 1, 4, 1. Or if the pair is 4, 2, then we won't include the pair 2, 4. Okay. These are the permutations. So now, if we are having these pairs, then what we have to do? We have to select the pair. Firstly, we have to do XOR of that pairs. Okay. So 1 XOR 4 will result in 5, and 1 XOR 2 will result in 3. 1 XOR 7 will result in 6. 4 XOR 2 will result in 6. 4 XOR 7 will result in 3. This will result in 5. See how? So let us see a table of binary conversion. See, if we are having decimal numbers 1, 4, 2, 7, 3, 5, then their binary conversion is this. 1 is equivalent to 0, 0, 1, 4 is equivalent to 1, 0, 0, like this. And if we have to perform XOR, then let us select a pair 4 XOR 2. Then how we will perform this? Binary equivalent of 4 is 1, 0, 0. Binary equivalent of 2 is 0, 1, 0. And what we have to do? We have to perform XOR. Performing XOR operation, this will result in 1, this will result in 1, and this will result in 0. So now 110 is the decimal equivalent of 110 is 6. 1 into 2 plus 1 into 2 plus 0 into 2, 0, 1, 2. So 4 plus 2, that is 6. So binary equivalent of decimal equivalent of this binary number is 6. So ultimately 4 XOR 2 will result in 6. So this is what we have written. So Now we'll check whether this result after doing the XOR, this comes in this range of 3 and 5 or not. So we'll check. 5 is in between 3 and 5. So this is 3. So result must be greater than equals to 3 and less than equals to 5. So this will count. This also will count. We won't count this. This will count. This will count. Okay. So there are 4 such pairs. Out of all 6 pairs, there are 4 such pairs in which after performing XOR operation, this comes in the range of 3 to 5. So for this, our answer will be, count will be 4. Okay. Now, if we'll think of the approach of solving this question, then the brute force method is what? Suppose we are given some number 1, 4, 2, 7, 9, 6 and we have to find such pairs in which after performing XOR this comes in a range. Okay, so what we'll think? We'll think that first select a number at index I and what we'll do? We'll start pairing with we'll start pairing this number, this integer with its forward indexes. Like if this is the ith position, then we'll XOR it with I plus 1, I plus 2 till n minus 1. Suppose they are the n integers. Then this is the indexing 0, 1, 2, n minus 1. Then what we'll do? If we'll select this number, then we have how many options? If we'll select this 0th position, then we have n minus 1 options. And if we'll select this one number, this at the number at 1th position, 1th index, then we have n minus 2 options to do the pair and we'll checking with each of them. And for the number at 2th position, we have n minus 3 options. Just like this, we will have only one option, that is this and this. So adding all these will result in basically summation of this will be basically this. So this will give something complexity of n square. Okay. So this method, if we'll solve this question with this approach, this brute force method, then it will result in time complexity of n square and we have to minimize this complexity. How we'll minimize this complexity? This is the brute force way. We'll implement the concept of trials. How? See, before moving to the implementation, let us discuss some points which we'll be using while implementing our approach. So these are the small concepts. So what are those? If we want to check two numbers, whether the numbers are in range or not. So see what we have to do. Firstly, we have to XOR two numbers and the result will check whether this result is in range or not. So for this, if we'll take two pairs like 4 and 2, then binary equivalent of 4 was 100 and of 2 was 010. Okay, so what we'll do basically, so we are checking for 4 and 2. So this is 4 and this is 2. If we'll have the most significant, bit of 2, so most significant bit of 2 is 0. This is most significant bit. So if we'll XOR this most significant bit, then the result will be 1. And if we are finding for the range less than equals to 5, that is 101. So what we'll do, we'll compare this one with this one. So are these is this number less than 1? So no, it is not less than 1. So what I am trying to say over here, that finding the XOR of most significant bit will not cannot decide whether the whole number will be less or smaller. See, before moving to this, first understand a thing. Like if we are having numbers 2, 3, 5, 9, this is number 1 and this is number 2. Like 4, and if we are asking which number is greater, then how can we find which number is greater? See, if we'll put 1 over here, no matter whatever comes after 1, doesn't matter. While checking this one only, we can decide that number 2 will be smaller than number 1. Okay, can we say that? If we are having a number 2359, 2359, and we are having a number which is starting with 1. Okay, suppose this will be of 4 digits and this will be also of 4 digits. I'm talking about the same number of digits for same number of digits. So if the number starts with 1, can we decide whether which number is larger and which is smaller? So yes, we can decide this is 1, no matter whatever comes after 1, this number 2 will be smaller. But if we say that the first digit is 2, then can we decide which number is smaller or greater? No, we can't decide because both the digits are same. Similarly, if this digit is 3, then we'll compare this digit. Here also we can't decide. But if this number is 4, then yes, we can decide. How? This digit is lesser than this digit. So we can simply say that number 2 is smaller than number 1. So if we have 6 over here, then also we can decide that number 2 will be, no matter whatever digit comes after 6, the number 2 will be greater than number 1. So this is what I am trying to say. So here also we will compare the same thing. If we have done the XOR of most significant bit, we have received 1. So can we decide here whether this number will be in the range of this or not? So we can't decide because this digit and this digit is same, for which we are comparing both the digits are same. Okay, now for 2, the next digit is 1. So we'll place 1 over here. This will XOR of these digits will result in 1. So now can we decide this number will be in the range or not? Yes, we can decide because on comparing these digits, this digit is greater than 0 and we have to find less than this range, within this range. So we can simply decide in this position only that this number will not be in the range. So we won't be checking for the next digits. Okay. So this is the efficient method to decide whether the number will be in the range or not. Okay. See, this we have decided for less than equals to 5. What if we have to check less than equals to 5 and also greater than equals to 3? Then for this, let us understand a thing. See, we have to find whether the result is less than equals to 5 and also greater than equals to 3. So let us focus on the thing that suppose we are given some numbers like 3, 5, 7, 2, 1, 8, 7, 6, 4, 3 and the low value is 4 and the high value is 7. And if we have to decide the number of the numbers, if we have to decide the count of numbers which are in between this range, then firstly what we'll do? We'll count the numbers which are less than equals to 7. So for that, less than equals to 7 numbers are 1, 2, 3, 4, 5, 6, 7, 8 and 9. So this count will be 9. And if we have to see, right now I'm discussing the brute force method to find the the numbers in between, count of numbers in between this range. So this is not the efficient method, but we are discussing to understand the efficient method more clearly. So less than equals to 7. Now we can do what? Out of all these 9, we can select the numbers which are greater than equals to 4. So that will be greater than equals to 4 will be 5, 7, 7, 6, 4. So such numbers are 1, 2, 3, 4, 5. So such numbers are among these 9 numbers, the range numbers will be 5. Okay, can we say that? But here we will use another method. What method? We won't be counting for the numbers which are greater than equals to 4. What we'll be doing rather than, we'll be counting the numbers which are less than equals to 3. Why 3? 4 minus 1. 3 means 4, whatever low value is, 4 minus 1. So what this will do, basically, if we'll count the numbers which are less than equals to 3, then what we'll be doing? We'll be subtracting these count. Whatever will come, in this answer, suppose the numbers less than equals to 3 are this one, 2, 1, 3 is also less than equals to 3. So this 1, 2, 3, 4. There are 4 such numbers which are less than equals to 3. Then we'll do what? For counting numbers greater than equals to 3, greater than equals to 4 and less than equals to 7, what we'll do? We'll subtract the count of numbers which are less than equals to 7 and count of numbers which are less than equals to 3. So basically this will give 9 and this will give 4. Ultimately we will be getting the correct answer, that is 5. Okay, so we'll be finding the numbers in range with this method. We'll be counting the pairs which which is less than equals to 7, and we'll count the number of pairs which result in less than equals to 3, and we'll be subtracting whatever we received from count of 7 with the count of 3. So now for this example, if this we have discussed for the general example, now we will be discussing the things for this example. So how we'll implement this thing? See, if we are checking for 1, then what we'll do, if we are checking all pairs of 1, that is 1s or 4, so let us move this thing. Okay, so we are discussing for this example. So if we will, firstly what we'll do, what we'll check for all 1 pairs, that is 1s or 4, 1s or 2, 1s or 7. And now for this, what we'll do, we'll count the pairs which are less than equals to 7, less than equals to 5, and we'll count the pairs which are less than equals to 3 minus 1, that is 2. So we'll subtract these things, and this will give the pairs which are in the range of greater than equals to 3 and less than equals to 5. So this thing we have discussed right now. Now we'll be discussing over this. So what we'll be doing, basically, see, in try, if we'll store these numbers, if we are checking for 1, then if we have stored 4 to 7, how will the data will get stored? See, firstly, if we see for 2, 0, 1, 0. So like for 4, 1, 0 and 0. For 7, 1 and 1. So now if we'll check for 1, that is for 1 it is 0, 0, 1. So how we'll check? We'll check the most significant first. Most significant bit for first. So this is 1 and this one is 0, 1, 0 is 2. Suppose we are checking for 4 first. Okay. So for 4 it will be 1, 0, 0. So how we'll check this thing? We'll check for firstly for 4, then 1 or 4. We'll be checking for the range less than equals to 5. So we are basically now checking for the count of less than equals to 5 range. So this 5 is 1, 0, 1. So firstly we'll do the XOR. So this will result in 1. So can we decide whether this will come in range or not? No, because this bit and this bit is same. Now we'll do XOR for this. So now can we decide? No, we can't decide because this bit and this bit is still same. Now we'll do the XOR for this. So now can we decide? No, because this is same. But now the number is completely scanned. So here this is equals to. So this will come in range. So here count will become 1. Means we have counted one such pair which comes in the range of less than equals to 5. Now we will compare for 1 and 2. So this will be 0, 0, 1. This will be 0, 1, 0. So we have to compare with 1, 0, 1. So 0, 0 will give 0. So can we decide this range, this will come in this range or not? Yes, this will come in range because this is 0 and it is less than. So we need not to do the XOR for rest of the digits. Here only we don't need to have this answer. We generally need this count. So we'll get our count from here only. We don't need to do the XOR for rest of the digits. See, it might come in the mind that this digit is not too long. Why are we putting so much effort in finding this XOR of rest of the digits? So it does, see, in this particular example, we are taking three digits, but it doesn't mean that always we will be having only 3 digits. The number can be, see, in the range of like 2000. So for 2000, we'll be having a lot of digits like 0, 0, 1, 0, 1, 0, 1, 1, 0, 1, such digits. Okay. So for finding at that time, for finding the XOR, for finding the result in the range, we need to have a lot more numbers. So this is the efficient method that instead of doing the XOR for all the digits, we can decide after doing the XOR for only 4 to 5 digits. Okay, so this will save the time. So that is why I was saying this is the most efficient method. Okay, so I hope you have got this thing. So now we will come back to our solution. So this will so finding the XOR of this most significant bit, we can decide that this number will be in the range. So count will become 1 plus 1, that is 2. Okay, previously it was 1, now it is 2. Now again checking for 1 and 7, 0, 0, 1, 7 will be 1, 1. So we have to check for less than equals to 1, 0, 1. So doing XOR for 0 and 1 will result in 1. So can we decide? No, we can't decide. So again we will do for second. This will also be 1. So now can we decide? Yes, we can decide. Here we will not increment the count. Why? Because this will not come in the range of 1, 0, 1. Here the this bit is greater than 0. So here count will still remain 2. It will not get incremented. Now we are checking for count of less than equals to 2. So for less than equals to, for the range of less than equals to 2, that is for 2, it will be 0, 1, 0. Now finding XOR for 1, 4, again 0, 0, 1, 1, 0, 0. So this will be 0, 1 will be 1. So can we decide here only that this digit will be less than, sorry, this digit is greater than this digit. It means this number will not come in the range of this. So now again for 1 and 2 similarly. So this will be 0, 0, 1, 0, 1, 0. So this will result in 0. So can we decide that this number will be in the range? Right now we can't decide because this digit and this digit is same. Now we'll do for this thing. Now can we decide? No, we can't decide because this digit and this digit is same. Now doing XOR, can we decide? Yes, now we can decide that this number is greater than this number. So this will not come in range. So for count of less than equals to 2, we don't have any count. Okay, still the count is 0. Here also count is 0. We haven't found any of the pair which is in the range of less than equals to 2. So now for 1 and 7, we will be checking 0, 0, 1 and 1, 1, 1. So less than equals to 1, 0, 1. Doing XOR, it will be 1. Doing XOR, it will be 1. Now we can decide that this number is greater than this. So this will not be in range. So count is still 0. So for pairing of 1, we have count equals to, that is of less than equals to 5, we have 2. Of less than equals to 2, we have count of 0. So basically we are having 2 such pairs. What are those pairs? 1, 4 and 1, 2. 1, 4 and 1, 2 are such pairs of 1 which are in the range of 3 to 5. Okay. So this thing we have discussed. Now for removing duplicacy, what we will do basically, we were having these numbers. So for the try, if we have done the work of 1, then we'll insert this one. Now we'll do what? We'll make pair for 4 and 1. So if we have 1, 4, 2, 7, then we'll do what? We'll do pairing of 4 and 1. Then we'll do pairing of 2 and 1 and 2 and 4. So how? If we have 1, 4, 2, 7, then we'll have 4 and 1. Then we'll have 2, 4 and 2, 1. And for 7, we'll have 7, 2, 7, 4 and 7, 1. So basically, we'll be having only 6 pairs. And after that, all the pairing are completed. So we'll be removing the duplicacy in this way. So for this question, we have discussed all the concepts which we'll be using in the code while implementing. So now let us implement the approach in our code. So this is our function of count pairs. So this is our num array of integers and low and high range. So we'll be returning our value of count, that is pairs in range, from this function only. So our first step will be, we'll be creating a root node. So what this node will be containing? This node will be containing a left and a right and a count value. So we'll be creating a class static class node. This node will be having a left of node type itself and a right. So we have to basically insert zeros and ones. So for 0, left will be pointing, for right, for 1, we will be inserting in right. And of count value. So count will be initially 0 and these will be initially null. So our next step is we'll be extracting the values from our integers. So from here, we'll be extracting values. So one by one, we'll be counting their pair in a range. So we'll call the function query. We'll pass the root in it and a high range and a value and one more thing, that is max bit. So what this actually max bit is, let us discuss. See, if you will read the question, then there is a constraint of that the number can be in the range of greater than equals to 1 to less than equals to 2 into 10 to the power 4, that is 20,000. So like in this array we are having numbers as 1, 4, 2, 7. So this number can be 20,000 also. Maximum it can go to 20,000. It can be 10,000 and 1,000. Like this the numbers can be. So to represent 20,000 we need 15 bits. We have to, if we have to represent this 20,000, decimal 20,000 into binary, then we need 15 bits. So for these 15 bits, to represent these 15 bits, we need 0 to 14 indexes. So for most significant bit, it will be representing as 14th index, then 13th, then 12th, and that last at 0th index. So in this, if we have to represent 1, then how we'll represent 1? Generally, 1 can be represented at 0, 1, or you can say 0, 0, 1 or 0001. So if we have to represent in 15 bits, then all bits will be having 0 and at last we'll be having 1. So to represent 1, we need to have these many bits. So this is why we'll be passing this max bit value as 14, because the maximum range can be go up to 20,000. So this max bit will be making it final because its value will never be changed. So we'll make this variable as final static variable. Static int max bit, which will be equals to 14. Now we are counting for the numbers generally for the pairs which are in the range of less than equals to high, and also we'll count for less than equals to, that is greater than equals to low. See, we have discussed a thing while we were in the explanation part of question. Then here we won't pass low, we'll be passing as low minus 1. Why? Because as we have discussed over here, for this we have discussed over here that to find for low value 4 and high value 7, we were finding pairs counting for less than equals to 7 range, which were equal to 9, and for less than equals to 4 minus 1, that is 3. And what we were doing to find the range between 4 to 7, we were subtracting from the range of less than equals to 7 minus less than equals to 3. So similarly, we are implementing this thing over here also. Okay. So this is what I was trying to say. And now after counting, we'll be inserting that value in our try. So basically now we'll be implementing our try. So we'll be making a function insert. We'll be inserting the value. Okay. and at last we'll be returning the count, whatever we'll receive from here. So now firstly we'll work on insert function. We'll see what this insert function will do. So this is function insert. So this will be returning void root and a value. So I hope you are familiar with the tries. So now here we'll be starting a loop from 14. Why 14? Because our max bit was 14. I greater than equals to 0, I minus minus. And here we'll be manipulating on bits. So I hope you are familiar with the basic bit manipulation. If not, then go and check the video. This has been discussed a lot more time. How we will be converting this into bits. So we'll do and with the mask, and if this value is greater than 0, then bit generated will be 1, otherwise will be 0. Okay. So now we'll check this bit. If this bit is equals to 0, then we have to insert in left. So we'll first check if root of left equals to null PTR. Then we'll insert this into, we'll create a node and attach it into the left of it. And now root will be pointing to left of root. Now if the bit is not equals to 0, that is if bit is 1, we'll be doing in right side. Copy this thing, paste it over here. We are doing for the right. We are attaching 1 at right and 0 at left. So we won't be discussing much on this. Basically, we'll be, see, we were also maintaining a count. So now count will get incremented. After attaching, count will get incremented. Initially it was 0. So here we have declared count. So initially it was 0. And here also we forgot to initialize count. So it will be count equal to 0. Okay. So now see this function insert, what this will do basically. We have given a root. We are given a root from get count function. Sorry. We are given root from count pairs function. We have created root with left and right having null and count equals to 0. So at that point we have created a root having left, having right, and the count equals to 0. So now at insert function, what is happening? If we suppose we were having elements 1, 4, 2, 7 in our array, range was 3 and 5. So if we have to attach 1 over here, if we have passed the value as 1, then what will happen? From I equals to 14, masking will be done and bits will be generated. So bits will be generated like this: 14 times 0, and at last there will be 1. Okay, but for now we are assuming that I equals to 3. Why? 2. Why? Because for this range 7 will be represented as 1, 1, 1, and to represent 7 in terms of binary we'll require only 3 bits. So we'll pass indexing as 2, that is I as 2. Okay, just for the sake of dry run, we are passing this as 2. Otherwise, in the question, it is passed as 14. Otherwise, our dry run will go too long. That is why I'm taking I as 2. That is, now we'll do what? We'll be attaching 1. How? We'll generate bits one by one. So bits will be bits generated will be 0 for 1 for my indexing from 0 to 2. Bits will be 0 0 1. So firstly we'll get 0 in our bit. If this bit is 0, we'll check. If left is having null, then we'll attach the 0 in our left, and now root is pointing to this, and count has become 1. Root was pointing to, sorry, root was pointing to left, and now root is pointing to root dot left, so count has become, see, here the count was 0, here initially the count was 0, here the count has become 1. Okay, so for the next time, when we'll come over here, when we'll be generating the bit again for index 1, then we'll get again 0. Now again this 0 will get attached over here, and count will become 1. Now again bit will be generated for indexing 0. For indexing 0, we'll get 1. So this 1 will get attached over here at right. So bit generated is 1, so it will come in else part. Here count will become 1. So now we have inserted 1 in our try. So this insert function is doing this task. So now let's move to another function. So other function was query function. So we'll be working on query. This query will be returning the count of pairs which are in the range of less than equals to high and range of less than equals to low minus 1. Okay, so let's create the function. This will be returning integer, that is count, and what we were passing in our query function. See, we were passing root, range, that is high, value, and max bit. So root, high, value, and max bit. High, value, and max bit will represent max bit as index. Okay, so here we have done something wrong. This will be root dot left, this will be root dot right. So now we'll be working on this query function. So firstly, what we'll do, we'll generate bits. For what? Firstly for value, and then for high. So generating bits for value and high. So how we'll do this? So this is basically bit manipulation. So value, we'll do and left shift 1 till index. Now if this value is greater than 0, then bit will be 1, otherwise bit will be 0. Same thing we'll do for this side, for generating bits for high. This will be high. Now we'll check the bits. If bit received, bit of value is bit of value is equals to 0, then we'll do some task. If this bit is 1, then we'll do some task. So Now we'll check if bit of high is also 0, then return whatever we get from query function, and a high and a value, and index will be decremented by 1. In else part, we'll return this will be root dot right. And also one thing, whatever we receive from count of the root dot left. So if you are not getting this thing, what we have done over here, then we'll be discussing it. First, let us write these lines. So we haven't written the base conditions for this. So if root equals to null, then return 0. And if index becomes -1, then we have to return the count of root. So we'll call this get count function, and we'll return the count whatever attached to its root. So we'll be creating a get count function also. We'll pass the root value, and this function will be returning integer value. If root is equals to null null, then return 0, otherwise return whatever is the count of root. Okay, so now we have written the base conditions and we have created the get count function. Now we'll see what this query function is basically doing. So let us do the small dry run over it. See, we have passed the root. So this is the reference to root. Initially count is 0. So this is the reference to root. This one is high value is 5. This was low, this was high. And value is, first value will be 1. Index is, see, index was passed as 14. That was max bit. But for now we have discussed that 7 can be represented as 111. So we need only 3 bits. So to 0.3 bits, we need 0, 1, 2 index. So we'll pass index as 2. Just for the sake of dry run. Okay. Otherwise dry run will get too lengthy. So we'll be checking the condition. So this condition will be false. Now we'll be generating bits for value, that is 1, and for high, that is equals to 5. So to represent them in binary, 1 can be represented as 001, 4 is represented as 100, 2 is represented as 010, 7 is represented as 111, 3 can be written as 011, 5 can be written as 101. Now if we have to see, we were working on the index 2. So for index 2 is, if we check 210, 210, indexing is like this. So at index 2, 1 will have 0. At index 2, high will have 1. So bit generated is 0, bit generated is 1. So if value bit is 0, then we'll check at high. If high equals to 0, no, high is not equals to 0. So we will get count of whatever is there in the left. Whatever is there in the left. So in this case, it will pass get count function. If we'll call this get count function, we'll pass root dot left, so it will receive null. So it will return 0. So we'll get 0 from here. Okay. So we are getting 0 from here. Now we'll again call write function, query function, and we'll pass root dot write. So this will also get null. Index will become 1, but this will encounter into this if condition. So this will return 0, and ultimately will return 0 from. Ultimately we have returned 0 for 5, 5, 1, and index was 2. So we have returned 0. This 0 will get received in the count of this. So this has received 0 for pairing of 1 with nothing, because see, first time we have generated for 1, so count was 0. Now again we'll call for, this was for less than equals to 5, for less than equals to 3, sorry, for less than equals to 2, that is low minus 1, 3 and 5. So for this we'll also have, again we'll have 0, because root of left is pointing to null and root of right is pointing to null. Now we'll insert value, that is 1. So we'll insert 1 in this. How? 0, 0 and 1. Its left will be null, right will be null. No, its left is not null, right is null. Okay, its right is null and its count equals to 1. And its left, right is not null, left is null, and count equals to 1. Its left is null, right is null. Okay, so count equals to 1. So now we have inserted, now we'll extract another value, that will be 4. So now we'll work for 4. So this time value is 4, high will remain 5, and index is 2, just for the sake of dry run. Now we'll be generating bits for value and high. So value is 5, value is 4, high is 5. See, basically this is first number and this is second value, and we are comparing with this high range. So we are basically judging for second value, that is whether these V2 can be all the numbers which are present in the try. So basically V2 is, for which we are checking is these V2s. Okay. So now for bit value at index 2, for 4 at index 2 we have 1. For 5 at index 2 we have 1. Now we'll check if bit v equals to 0. No, bit v is equals to 1. We'll come in else part. We'll check for bit h. Bit h is also 1. So we'll get count of root dot right. So root of right is having null. So this will return 0. Now we'll query for root of left. So we'll have 0. High will remain 5. Value will be 4. And index will become index minus 1. That is 1. Initially index was 2. Now we'll call for, we'll come and enter into this function again. Now we'll check these conditions. So root is still not equals to null. So we'll generate bits for index 1. Now for index 1 we'll generate bits. So for 4 at index 1 is 0. For 5 at index 1 is 0. Now we'll check if bit v is equals to 0, bit h is also equals to 0. Then we'll call root dot left. So we'll be calling root dot left. So calling root dot left with high, value and index minus 1. Okay, again we'll come into this function query. Now we'll check both the conditions. Now we'll generate bits for 0th index. For 0th index, 4 is having 0, 5 is having 1. Now we'll check if bit v equals to 0. Yes, bit v equals to 0. Bit h equals to 0. No, so we'll come in else part. Now we'll get count function from root dot left. So root dot left is pointing to null. So this will return 0. Now we'll call root dot right. So root dot right function will get 1 comma high. High is still 5. Value is 4. Index is now minus 1. Now we'll call this function. Again query. Recursively we are calling query. So we'll check the condition if root equals to null. No, root is not equals to null because root is pointing to 1. Now we'll check if index equals to minus 1, get count of root. So index equals to minus 1. Yes, this condition is true. So we'll return what? Get count function. So whatever we'll receive from get count function. So get count function will have root as 1 and 1 dot count. Count of 1 is having 1. So this will return 1. So from here we'll get answer as 1. This one will get returned to this. This one will get returned to this. This one will get returned to this. And ultimately we'll return 1 from here. So we'll receive count as 1 over here. So basically we have queried for the pair of 1 with 4 with rest of the numbers present in the trie. So trie was having only 1. So for 1 XOR 4 we have received an answer which is less than equals to high, that is 5. Okay. So now we are not doing the rest of the drawing. We will be discussing what we this now how these calls will work. So we have called for firstly for 1. So this try was having nothing. So we have received 0 from everywhere. Then we have inserted 1. Then we have called for value, second value, that was 4. So 4 was XORed with 1 and 4 was XORed with 1. And this has returned something which was in the range of less than equals to 5. So there was a value of count. So here count we received was 1. Now what happens? Now 4 will get XOR with 1 and we'll receive some count. That count will result in for less than equals to low minus 1, that is 3 minus 1. So 2. Now we'll get value as 2. Now what will happen? 2 will be XORed with rest of the digits. So rest of the digits, now 4 was inserted. Now 2 will get XORed with 4 and also 2 will get XORed with 1. Whatever is inserted in this try for less than equals to 5. Okay. So we'll receive some count from here also. Then again we'll receive, then 2 will also get inserted. So by this time one more thing is left. One more call was there for 2 XOR 4 and 2 XOR 1 for less than equals to 2, less than equals to 2. Okay. So this is count plus call. This is count minus call. This was count plus call. This was count minus call. Okay. Now here 2 will also get inserted. So by this time we have 1, 4, 2 inserted in our try. Now we'll receive a value 7. So now 7 will see after this I'm writing over here. Now 7 will receive 7. Now we'll XOR 7 with rest of the pairs, that is 7 XOR 2, 7 XOR 4, 7 XOR 1 for less than equals to 5 range. Okay, so these values will be counted as in plus and then this will be in a single call of count plus. This will be in single call of count minus. So 7 will get XOR with 2, 7 will get XOR with 4, 7 will get XOR with 1. Okay, for less than equals to 2. and after this our values will get finished. So from here we'll be counting, maintaining the count, and at last we'll returning the count. So why we are finding 5 less than equals to 5 and less than equals to 2? So this thing I have told you, this thing we have discussed over here. See, for the range of 4 and 7, 4 and 7 we were finding count of less than equals to 7 and less than equals to 3, and we were subtracting this thing. So same thing we have done over here. So this is how we'll receive our answer. So now we'll be running our code. See, we haven't done the dry run for the whole input, but I hope if you need to do, then you can practice on your own. Now you will be able to do it. Okay. Otherwise it will get too lengthy. So there is some errors. Line number 51. Okay. So okay, so I have written null PTR, which will be null. Basically in C++ we use null PTR, that is why my fault. So accepted. Let us now submit it. Check all the test cases are passed. So okay, all the test cases are passed. I hope you have understood the concept and the question very well. See, if you know, as I told you, if you need to practice the dry run, then you can do on your own. We have just, I have told you approach to do the dry run. Best part, I hope you will be able to do it. So thank you for watching. We'll be meeting in another video with another question.